Hello everybody. Now I'm going to focus on the complex Fourier series. So basically the goal I have here is take off the typical Fourier series that we have and have them represented in a complex form, or sometimes it's also called exponential form. Okay. But in order to go there, I just want you to remind you, because I have covered this before, it's called the Euler's or the Euler's formula, where this is e to the power of ix is equal to cosine of x plus I sine of x. This may feel familiar to you because when I was covering higher order differential equations, specifically the homogeneous linear equations with constant coefficients, we had several cases. One of the cases were the complex conjugate roots, and I used this Euler's formula right there. Okay, but I will now use a little bit more often than that, and I want to focus on e to the power of minus ix. So you will see that this is going to be cosine of minus x plus I of sine of minus x, right? And we have covered this in the previous Fourier sine and cosine series, that cosine is an even function, which means that I will get myself cosine of minus x is equal to cosine of x. However, on the other hand, this sine component is odd, so I will get myself this relationship. Okay, let's actually add this one and this one. What will happen is these two will add up, but these two will cancel each other because one is plus I sine x, the other one is minus I sine x, right? So I can actually use that to express the cosine in this manner. Cosine of x will be equal to e to the ix plus e to the minus x ix divided by 2. Okay, I can do a similar for sine because I want to obtain sine as well. It's not enough to have just cosine. But what I should do then is I need to have this minus this, right? If I have minus, cosines will cancel. I've got 2i times sine of x is equal to, right? So from there I will get myself sine of x will be e to the ix minus e to the minus ix by 2i. Don't forget the I. So, okay, I think I am ready to plug this into my Fourier series expansion that we have established already. Okay, and here is what it was looking like. F of x is equal to a0 by 2 plus, I had this from n is equal to 1 to infinity. I have this an cosine n pi x by p plus bn sine n pi x by p. I'm sure by now you memorized this already. Let's express this in the exponential or complex form. So I will get myself a0 by 2, which I can't do much about it. There's nothing going on there, but I will have something happening over here, an times. Now, cosine, I'll simply pull this from here and plug it in there. Okay. Remember that though. This in here, the x is not just simply x and pi x by p, right? So I'm gonna use that over here and over here too, right? Okay. Let's continue. So I will have e to the power of I n pi x by p plus e to the power I minus n pi x by p divided by 2. That's what I have, right? So this is the first. Plus bn times, I'm going to write down because I ran out of space. So I will simply copy paste from the sign. It will be e to the power of I n pi x by p minus e to the power of minus I n pi x by p divided by 2i. Again, I'm repeating myself, but actually properly, let's write this negative down here, right? Don't forget this I. I've seen this many times, okay? And I should close the parentheses. So basically, this is what is happening. A0 plus this. So the next step that I will do is I will actually get the in parentheses of e to the power of I n pi x by p, and in another parentheses by the negative of it. All right, so let's just establish that. So I'll get myself a0 by 2 plus summation n is equal to 1 to infinity e to the power of I n pi x by p times, I'll get myself a n by 2 plus b n by 2i, that's the first one, plus I will have e to the power of minus I n pi x by p, parentheses again, an by 2 is the same, but this time it's going to be minus, not positive, bn by 2i. Okay, so that's what I wanted to establish. So now I will actually rename these. So what I want to call this is, I want to call this C0. So I'm looking over here. Did you realize that these are complex conjugates? you know. So if I call this Cn, I will call this C minus n, right? N is basically, being consistent. This is n, right? So I'm saying that this is the Fourier series coefficient. It's a complex, right? Obviously it's a complex. There's an I over here. But looking at it, the only difference is there's a negative sign here, there's a positive sign here, so there's a complex conjugates, right? So I want to just simply write that. But now, okay, let me just write one more line and then show you something. I have a point, wait for me. C0 summation, you will like it, e to the power of I pi n x by p plus c minus n e to the minus I pi n x by p, okay? So now question is, can I write this in a much more compact form? Because looking at here, I have n 1 to infinity. And if I put 1 to infinity over here, this is actually from minus 1 to minus infinity. Do you see that? So this is from 1 to infinity, minus 1 to infinity. And I even have a C0 times, if I put n is equal to 0 over here, what will happen to this term? This will be 1. Okay? So what I mean is, this is the zeroth Fourier series expansion coefficient. This is the plus ones. These are the negative ones. So I can combine all three of them into one single phrase, which I think you will appreciate. So my f of x expansion will go from like this one now, minus infinity to infinity. Cn, just wait, I will explain. I pi n x by p. Okay? So obviously I want to highlight here is n is 0, n is plus minus 1, n is equal to plus minus 2, and etc. Right? It goes all the way to infinity. Okay, I think this part you kind of get, but this part you may be a bit, where is this coming from? Well, let's plug n is equal to 0. What will happen to this term when I plug n is equal to 0? This becomes 1, right? So what I'm left with is c, n is 0, 0. So this term is captured already, okay? So I can put plus minus. So this entire, if I go up here, I will show you right here. So instead of writing this, I'm going to write that, the pink color. So it's much better, right? Obviously, I need to do something about these coefficients though, okay? Because I didn't really do anything about it, right? So let me go have a stab at it and see where I end up with, okay? I will still go ahead and use the fundamental definition that we have established. The C0, be careful that this is A0 by 2. That's what I called, okay? So that's going to be 1 by 2p, okay? Minus p to p, f of x dx, that was what it is, okay? On the other hand, I can have the Cn this way, 1 by 2. I'm simply, I'm going up, I'll show you. I'm simply writing this, rewriting that, okay? I just take it in one half parentheses. An plus bn by I, right? That's what I have. So I'm simply multiplying by I. So plus bni divided by I squared, okay? So what is I squared then? Right over here, what's I squared? That's minus 1, right? So then I can write this way, 1 half an minus bni. Make sense? Actually, now what I'm going to do is I will go right back to the definition of an and bn. We already established that. Remember, we had so many problems about it. So I'm simply going to insert that right over there, 1 half. Okay, an was 1 by p integral minus p 2p f of x cosine n pi x by p dx minus I times the bn, and the bn was again 1 by p integral minus p to p f of x. This time around I'm multiplying by sine n pi x by p dx. I run out of space over there, okay, and I need to close the parentheses here. Okay, the only thing that I can do over here, I can see that each integral, there's integral limits are the same, and each of them is multiplied by fx. So I'm going to combine the integrals and write one integral, which I can do. I mean, it's not groundbreaking. 1 over 2p, I can take p out of, minus p to p f of x. Now let's see what happens. Cosine of n pi x by p minus I sine n pi x by p dx, right? So if you wanna distribute this, you can see you can distribute this term is that term, minus I term is that term. So just to verify that we're on the same page. Now this is actually, you may see this, remember if I go back up here to the very beginning of the segment, see So I'm going to use this Euler's formula to insert it over there. And basically this is e to the power of negative, because there's a negative sign in front of it, minus I n pi x by p. That's what it is, this, this term. So now, if I rewrite this for one last time, I will get myself Cn to be 1 by 2p integral minus p to p f of x times e to the minus I n pi x by p dx. And just remind us, this n will be from 1 to, and I will go all the way to infinity. Okay? Now I need to do the complex conjugate of it. Let's change color because it's kind of getting a little bit long and getting a little bit tiring for all of us involved. An minus bn by I. I'm simply copying, from here. Where is it? Right here. Right here. I simply copy and write it down here by just factoring out 1/2. Okay, I will do the very similar approach. I will have an plus, why plus? Because when I multiply I, the denominator becomes I squared, which is minus 1. I bn, okay, and I will plug the same thing that I did before, except I now know the an and bn, so it's going to be 1 over 1 by p minus p to p f of x times cosine n pi x by p dx plus I times the bn, which is 1 by p minus p to p f of x sine n pi x by p dx. Okay, and I need to close one more parentheses. So I will do exactly the same approach that I did, 1 by 2p minus p to p. F of x is common between those two integrals. Then I will have myself cosine n pi x by p plus I sine n pi x by p dx. And just like I did before, from the Euler's equation, this is going to be e to the, this time around it's going to be positive I n pi x by p. Okay, so if I go back up here, I will write minus c minus n will be 1 by 2p integral minus p to p f of x times e to the I n pi x by p dx. In this case, just to remind you, this is again, n is, because I have a negative in front of it. That's how I define this. So I'm almost done with this segment, but I'll do one more slick move, and you will appreciate my slick move. I can combine this, okay? Because you can see it's the same logic that I did before. Compared to this and this, the equation looks the same, except there's a negative n, is negative value over here. This and this can be combined, plus C0, where's C0 here as well. So let me write you what it is at, then I will come back and revisit this momentarily. Okay, let's write this way. Everything can be written in a very compact form this way. F of x is equal to, so now this goes from minus infinity plus infinity. I will have Cn e to the power of I n pi x by p. I showed you this already. Okay, this I didn't show you because I'm taking a shortcut. It looks like clear to you. Minus p to p f of x e to the minus I n x pi by p dx. But this time around, I'm going to say that n is equal to 1 plus minus 1 plus minus 2 all the way. Okay, so let me explain where this very last one comes from. You can see over here that there's a negative n, right? If this is negative, then this negative becomes positive. So it's actually this equation. So this represents the negative half of it. How about the positive half of it? Well, it is literally what I wrote there, down there, except that the answer is different, so that is captured. How about C0? What happens to if n is equal to 0? Well, if n is equal to 0, this term becomes what? 1. 1 by 2p integral fx dx. So let's look at C0. Bam! That's captured too. So I capture everything by this, what is this color? Purple-ish font. So this is what you need to know, this whole thing from this segment. And I will apply this to some example problems, okay? Thank you for watching this derivation of the complex Fourier series. I'll be right back with some examples.